Let us discuss moving through space-time. How do we can move through this time and space graphs? We know about three spaces, X, Y, Z. Easy to conceive the idea. Fourth dimension is the time. So it's space plus time. And in the time and space diagram, we cannot go like this because this means that we are going backward in time, which is not possible. Similarly, if we look into this diagram, this 45-degree straight line corresponds to the speed of light. I have already discussed this in my special theory of relativity video, which tells me that this region is forbidden. Because if I want to travel anywhere in this region, that means that I am traveling with a speed which is greater than c. This region is okay. I can travel with the speed, with any speed less than c, but not greater than c. What will be my movement in the space time, or rather time space diagram? Suppose I am here. This is my home. I wake up in the morning and then I get ready for my destination, for my institute. My place is not changing because I am still at home. My clock is ticking. Time is going. Then I change my coordinate. Time and space both increases. Then I reach my institution, my college, and then I stay here. Here my position does not change, but time increases on its own. Again I am coming back to my home. Again my position is not changing. Time is going upwards in the positive direction, always. Let us draw the time and space diagram, but in a little complex way. This is my time axis going always in the positive direction. This is position axis. I can go right, I can go left. These straight lines correspond to the velocity of c, the speed of c, 45-degree angle, straight line. This region is past. This is forbidden for me. I cannot go back. I cannot go in the negative direction of time. This region is future, and this is now where I am standing here. This point is quite inaccessible, rather inaccessible, forbidden for me. Like if this is Delhi, I cannot reach this point. Because if I have to reach Delhi from Kolkata, Delhi is here, which means I am going with a speed greater than c. Here we can see that dx is change in coordinate is very much, and correspond to that change in time is very less. And we know v equal to change in position by change in time. Here obviously in this region, position changes far more rapidly than time, which means a speed corresponds to a greater speed than light. So this region is inaccessible to me. If Delhi is here, I can reach easily. This is quite accessible region, quite accessible point for me. Because this region, reaching at this point requires for me to travel at a speed lesser than c. Coming back to the reference frames again, suppose I am here. I am describing an event. I note I am here, I am describing that the position of the event, that is where the event is located in the time and space diagram, is at P. Position change is delta x, correspond to the time change, which is delta t. and v is equal to del x del t. So for me, the velocity of the event is del x del t. If someone is traveling with a spaceship inside a spaceship spacecraft which is moving at a speed v, and v is comparable to the speed of light, and he or she measures the coordinate, the time of the same event as del x prime del t prime. So we know that in both the reference frames, the measurement of this del x and del x prime must not be equal. Measurement of the time intervals must not be equal, but there is a relationship between them. Following this relation, this I have discussed in special relativity section. Similarly, for del t prime, I have this relation. So for this kind of diagram, where I am sitting here and observer is sitting here with inside a spacecraft moving with speed v, I want to find out this quantity, this c del t prime whole square minus del x prime square. I would like to see what will be the value of it. Del t prime is the measurement of the time interval measured by this person inside the spacecraft. Del x prime is the measurement of the space interval measured by this person moving with speed v with respect to me. Let's see what is that. I'm just making a substitution for del t prime and del x prime, and then I'm doing some algebra. This is nothing but a minus b whole square, a minus b whole square. So I am just writing down in the formula. Here are some algebra. One thing is this c square c to the power 4 get cancelled out. We have c square here only in the denominator. C square in the numerator, c square in the denominator cancel out. So it's minus 2 del t v del x plus 2 del x v del t. These two are getting cancelled out. So these two expressions are getting cancelled. I'm left with this. Then again making c square, again taking out c square from this parenthesis and having a minus sign here in front of del x square. I have reached this place. So what I got is this one, c del t whole square minus del x square, and this is equal to c del t prime square minus del x prime square. From equation 16 of my special theory of relativity, this is nothing but s square. So there we have already told you that s square is independent of the reference frame we have chosen to measure the position and the time interval. So s square is an invariant quantity. Whatever be my reference frame, whatever be my measurement of time interval and displacement or distance, this quantity s square must be invariant, or rather is invariant of the reference frame. So we have already calculated that s square, which is ct square minus x square, is invariant of the reference frame in which we are measuring s square. Now, what will be the shape of this s square? S square will look like this red hyperbola. For each and every point in the hyperbola, the value of x and t will be different. But if we put those values of t and x into s square, we'll find that s square for all the points on the red hyperbola remains constant. And the object is moving along this hyperbola with the different coordinates of space and time. And we may call this that the object is moving in a Minkwoski space. Now, what if an object is moving in this reference frame? Suppose the coordinate of any object is p at a certain time. In the meantime, the object has traveled a distance delta x within a time interval delta t. So the speed of that object is v equal to del x del t. Now, suppose I am moving with a speed of 10 km per hour. Someone is standing at the ground and he or she is observing me. For this person, I am moving with a speed of 10 km per hour, but for myself, I am not moving at all. I am at rest with respect to me. What will be the value of s square, which I calculate? This would be s square. I calculate s square according to this relation, s square equal to ct square minus x square. As I am not moving with respect to myself, so the distance traveled x is equal to 0. So here I can find s square equal to ct square, which means s equal to ct. So for me, I am traveling with a speed of 10 km per hour with respect to some other person. Now, what will be the value of s square with respect to that person? He or she will measure different values of x, that is distance, and the different values of time. Suppose, according to that person, the distance traveled by me is x prime and the time interval he has calculated or she has calculated is t prime. So, for that person with respect to whom I am moving with a speed of 10 km per hour, s square is equal to ct prime whole square minus x prime square. As I am moving with a certain speed v, and we know distance equal to speed into time, so x prime is equal to v into t prime. So here we get ct whole square minus v square t prime square. From this, I can readily calculate what is the value of t. Now I am dividing both sides by c square, and I am getting t square equal to t prime square into 1 minus v square by c square. So t is equal to t prime into 1 minus v square by c square. And this is the relationship we have already calculated in our special theory of relativity. Now, what will be the speed through the space-time? Suppose I am at this position. I'm not changing my position, but I am moving along only this time axis, and as x has a dimension of length, so in order to make t as the dimension of length, I have multiplied t with c. So the distance I have traveled along the time axis within a time interval t is ct, but that is only along the time axis. So the speed thus is calculated, speed equal to distance by time. Speed is c, speed of light, which is constant. So if this is the situation where x is not changing and the object is moving with along the time axis only, then the object is moving with the speed of light, that is c. Now from the universal quantity, one thing I would like to mention, that what is c? C is the speed of that person in space time. I am not telling that it is moving only in space. The movement is in the space time. And what will be the value of the universal quantity then? As the person is not changing its x coordinate, so s square is equal to ct only, because x is equal to 0 here. S by c, that is distance by velocity, is time. We call this tau because this has a special significance. This is a universal constant. Everybody will measure this tau same, because as s square is independent quantity, s is also invariant quantity irrespective of the reference frame. So s by c is also invariant irrespective of the reference frame. So tau is something, tau is a time interval in which everyone will agree, and this is called the proper time. And this is the longest time we could ever measure. Proper time is the time calculated with the watch in my hand. Except that watch, all the other watches which are moving with respect to me are slowest. Now what will be the how I can divide the portion of the velocity between the space-time. Suppose it is not at all moving in this axis, that is in the x axis. So it's moving only in the time axis with a time interval of delta t. This is the proper time, and that object is moving with a speed of c. But what if that velocity, some portion of the velocity is wasted or is spent for traveling along x-axis also. So here, if the object is moving like this curved path, it has a space coordinate and it has a time coordinate also. This is x space, this is time. This thing is like that. Suppose I am moving from my home, I can move like this towards north, 100 meter, it's okay. I can move like this, 100 meter towards east, that's also okay. But when I am traveling like this, I am traveling in both north and east direction, because if I look into the tip of this arrow, then it has a certain position coordinate and certain time coordinate. Everyone is moving in the space-time diagram. And travel with the speed of light, which means traveling along the time axis only with the speed of light. If you travel with the speed of light, you will be forever young, because then your clock will be the slowest forever. Now we will investigate the speed through space-time. Suppose our observer is moving only along the time axis. He is not moving at all along the space axis. If we multiply time with speed c, we'll get the same dimension of distance, because speed into time is distance. So here the entire velocity is c, and the observer is moving only along the time axis. Now speed is easily calculated, because speed is equal to distance by time. Distance is equal to ct meters along this time axis, and that distance ct is travelled within a time interval of t seconds. So ct by t, I'll get the speed c, which is the speed of light in vacuum. This is the speed of the observer in space-time, not along space only, but in space-time. Now let me tell you what is the universal quantity s square, because already we have shown that s square is invariant of the reference frame. Now s square equal to ct whole square minus x square. As the observer is not moving at all, along this x-axis, so x must be 0. If we put x equal to 0 here, I will get s square equal to ct whole square, which means s equal to ct, which in turn gives me s by c equal to t, which is time, that is distance by speed, which is equal to time, and that is equal to tau. S is universal constant, because s square is universal constant, so s is universal constant. C is the speed of light in vacuum, so it's universal constant, which gives me tau as universal constant, which means everyone will measure the same tau, and tau has a special name which is called proper time, and that is the longest time interval. Longest time interval is tau. For me, as I am traveling along this time axis, I am holding a clock in my hand, and the time measured in my clock should be equal to tau. If someone is moving, if someone is standing here and he is observing me, I am traveling with the speed c. So for this person, this clock will be slower, rather the slowest, because it is moving with a speed c, which means if I am traveling with speed c as seen by this observer, and this observer will infer that my age increasing, increase of my age has been stopped. I will remain young forever, according to him. Let's find out the clue of the fact that the space-time is curved. If some object has acceleration, then its path of movement in this space-time diagram will be like this, because this shows f is the acceleration of the object. This shows for a smaller increment of time, every time this distance is increasing progressively. So instead of going into a straight line, the object is actually traveling in a curved path like this, because with the distance, with the increasing time, the distance is increasing progressively. Now let's think about the equivalence principle, which will give us a clue of curvature of space-time. Equivalence principle tells us, this I have already discussed in my introduction to general relativity video, Einstein told that if someone is standing on Earth experiencing the gravitational field, gravitational force of Earth, G, then that frame is equivalent to a rocket, equivalent to the observer inside a rocket, and that rocket is accelerating with an acceleration G. And for acceleration, this type of curved path is stressed out by the object, and from the equivalence principle, if this type of path, this type of trajectory is experienced by this one, so this person will also experience this curved path because of the principle of equivalence. Now let's think about this universal quantity s square. We already have shown that s square is an invariant quantity. No matter in which reference frame we are standing in, we know that s square, which is ct whole square minus x square, is independent of the reference frame in which we are calculating it. If someone is moving like this in a straight line at a certain time, it has also a value of x, and for this straight line t increases and x, that is the distance, increases in equal amount as t increases. So for this type of travel, if I plot it like this, s is actually a distance because ct is speed into time, which is distance, x is distance itself, so distance square minus distance square is distance square, so s square is distance square, so s is a distance. For this type of situation, if s is the distance from origin to the final point, then applying Pythagoras theorem, we could easily write that s square equal to x square plus c square t square, like this. But we know that this is actually correct form because this thing is actually invariant. And if we plot this, we will get a hyperbola. For every point on the hyperbola, if we join all the points to the origin, all the distances are not same. Every distance is different from its neighboring one. But if we calculate s square, we will get that is universal. Everyone will calculate a different value of x and t, but everyone will agree that s square will be the same. This is another hint. And from the equivalence principle, we can conclude that acceleration and gravity, acceleration in this rocket and the effect of gravity, both are same. So acceleration and gravity has a curved effect on space-time. But what causes gravity? We know it's mass. If we consider flat space-time like this is a flat one, and if we drop something, put a mass here, I will get a depression here around this object like this. So because of the presence of object, this flat space-time is curved. Same thing happens for the light also. Light thinks that the space-time is flat. First it goes like this, but when it reaches this point, it will take a bend. Just like a golf ball, when it reaches the rim of the hole, it travels in a curved path along the rim and then goes to the hole. Suppose, just give me an example. We know that we have curved lines which denote the longitude of us. These are stretched from North Pole to the South Pole. We have another great circle, which is the equator. If someone stands here and someone stands here and here also, and they started a journey and they're going to North Pole, they will think that they are going along parallel lines like this. But when they reach North Pole, they will meet together. So they may conclude that there must be some force which is pulling them together, which causes them to meet, but there is no force. That is because of the curved lines. They are actually moving along some parallel lines, and then they find that they meet together. And why they meet? Because of the curved lines. So gravity does not exist at all. Einstein's general theory of relativity makes us think like this, that gravity does not exist at all as we understand it. It is just an illusion. And it is because of the straight lines in curved space.